So Matthew Danish, why don't you come on and tell us a little bit about who you are and a little bit about this company that's making pipe down in South Carolina.
Hey, yeah, my name is Matthew Danish. I'm with Agro America. Agro America is honored to be a sponsor of this PE Alliance webinar, and we appreciate the opportunity to tell people about us and about using HDPE pipe. HDPE pipe has been around for a long period of time, and it is going to continue. It's basically the only pipe system really that's actually growing, where most other pipe systems are decreasing in sales across the U.S. So Agro makes large diameter pipe from 24 inches up to 10 feet in diameter for ocean going transport to putting on any kind of truck and shipping it all over the country and all over the world. Agro's been in business for over 50 years. We've pioneered the large diameter pipe system with the fittings that go with it, including electrofusion couplings and ocean towing across the world and flat racks around the world of large diameter pipe and all different types of piping systems that from anywhere from potable water to chemicals and industrial plants.
Yeah, some of the really cool projects, Matthew, are like you've been working on some fantastic outfalls, and you guys invited me to your plant last year, and I saw that my first 63-inch DR11 pipe.
Yes, that's another, when you're making large diameter pipe, thicker walls is something that is part of the game. So you understand how to make large pipe, you understand how to make thick wall pipe. And so, yeah, we first started making large pipe and they said, hey, well, you know what? We can actually make smaller diameter pipe in really a great thickness material with higher pressure requirements. And so now we're able to go into the markets, expand the AWW range of your SDR9s up to 63-inch now.
Yeah, that's fantastic. Congratulations on that. And we've talked on this channel a lot about why you have the ability to do that. And that has to do with low slump resin. So we take those resins and we extrude them to that thickness, but you've got to hold that thickness. That's kind of a half art, half science, isn't it?
That is right. It is it's something that you have to understand how the plastic flows and what it does when it starts to cool. So you have to not only cool it, but hold it properly during that whole process.
Well, we get a lot of engineers on this webinar program, Matthew, and they don't necessarily always pay attention to, why is it, what's the technology behind our ability to make thick wall pipes. But guys like you that educate us, we're so thankful for that, because many engineers want to know the why behind the product itself. So that's one of the reasons we do this. So thank you very much. Anything else you want to add?
No, that's it. Enjoy the presentation. And if you have any questions, just put them in the comment section.
Awesome. Yeah, questions in Q&A. And Matthew, if you could help us on the bench today, that would be awesome. And then come on screen when you want to add to something John, Ryan, Alan, or I are talking about. So thank you, Matthew Danish and Agro. All right, now, John Shumchick, could you come on and say hello, please?
Hi, guys. Can everybody hear me?
You betcha. We can hear you, John. Tell us who you are and what you do.
Sure. Thanks, Peter. Yeah, hi, I'm John Shumchick. I'm the Executive Vice President here at Eastern Utilities Services, which is the directional drilling division of the Haugland Group. Haugland Group is a general contractor out of the New York tri-state area, and I handle the directional drilling for them.
Yeah, we're going to hear about one of your very cool projects today. You're helping run electricity from the province of Quebec down to Manhattan.
That's right. Yeah, Champlain Hudson Power Express is the largest renewable electric project in the country for the past year and a half. And we were lucky enough to be one of the directional drilling contractors on the job. So
using HDPE pipe.
Correct.
Fantastic. We'll see you in a minute, John. Thank you for being here today. Ryan Ruiz, come on out and say hello, please.
Hello, everyone. My name is Ryan Ruiz. I am the regional sales manager.
Okay.
Sorry, there's my video. Sorry about that. Ryan Ruiz. I'm ISCO's regional sales manager based out of Texas, Dallas-Fort Worth area. I cover the municipal market here for ISCO, and a little bit about ISCO. We're one of the largest HDPE distributors in the country. We have roughly 40 locations in North America, including Canada, and we distribute things like pipe, fittings. We have fusion equipment and things like that. So here to help represent ISCO and the PE Alliance today.
Good. Thank you, Ryan. All right, next slide, Alan. So yeah, the social media program is strong. Here are the contacts. You may want to take a snapshot. This would be good. You want to get a hold of the Alliance or Matthew, Ryan, or John, right here. This is the slide to take a picture of. We get a lot of cases and leads out of these and help people with their polyethylene projects. And with that, Alan Ambler, I'll turn it over to you.
Awesome, Peter. Thank you so much. I'm glad everybody knows kind of sort of the drill. Matthew talked about the questions that we get. Those questions you type into Q&A, and then there's a whole team of people behind the scenes to run that parallel program with you. We've had some questions even before the webinar started, so that really certainly helps us be able to cater the program specific to your needs. Now, remember, we've got a strong bench that are behind the scenes that are there to really help you and answer all those questions as we go through. So, yep, come on back, John. Let's take a look at pilot hole for the horizontal directional drill. Why don't you tell us what's going on here, John?
Sure. So, big picture of directional drilling is you want to be able to install a pipe past an area you can't open cut. That's really the purpose of it. So you hear in this picture, you've got a body of water. You could replace that with a highway, set of train tracks, sensitive area, sensitive neighborhood, sensitive environmental area, and you need to get your pipe from one side to the other. So if you notice the entry pit there, you'll get a little bit better picture when we get to some of the photos of the drills. But for instructional purposes here, the entry pit is where the drill rig is set up, and the drill rods are pushed through, down through the ground, at the desired angle, down to the desired depth, and come out on the exit side. The real benefit to directional drilling over something like a jack and bore or a microtunnel is there's no shafts, right? The drill rig and the entry pit and the exit pit are both on the surface. So there's no need for dewatering, there's no need for supportive excavation. Everything starts and ends on the surface, and with the steering and the bend of the drill rod and of the product pipe is how you achieve your installation. So HDPE being a perfect example of that, can bend in pretty miraculous ways, and that's why it is our preferred product to install with the drill.
So this is an intelligent process as well. You can control that tool as it's being drilled into the ground for the the direction or the profile, the horizontal, all those types of things. You have accurate control over where that initial bore path is going, correct?
Correct. Yeah, normally for a larger diameter drill like the one you're showing here, under a body of water, you would have all that geometry and surveying done before you arrive. And you'd set up either a wireline grid or a gyroscopic locating system. And then, the drill rod and the steering tool, as you're shown here, would use that magnetic coil and be triangulated throughout the pilot bore process. So you can, as Alan said, it is steerable. So you're heading down at a 10 to 20 degree angle. When you reach your desired depth, you steer it so it's flat. And then when you want to come back up, you steer it up, and it comes out on the exit side. So it is a very, very accurate steerable process.
Okay, so after that, we expand that borehole, and there's certain mechanisms to do that expansion. Can you elaborate on that process for us some?
Sure. When the pilot hole is done, the pilot tooling is removed, and depending on your size of your product, you install the appropriate size reamer. The reamer expands the ground as you pull it back. And while that's going on, there's drill mud that's being pumped through the reamer. That drill mud actually carries the displaced material out of the hole. So if you'll see here on the back side of the reamer, that large area that's being opened up, all that dirt that was there is being carried back out to the exit side by the drill mud you're being pumped. And then it's being sucked up by either a vac truck or a reclaimer, reprocessed to be sent back to the drill so it can be recycled and used over and over.
All right, so that reaming process, we're removing material, correct? And then it stays suspended within some type of fluid, your bentonite or whatever, goes back to a location as to which you're filtering out that material that we're removing, and then continuing through that process. So we're essentially underground taking out material through that, processing it, and removing it from the bore path as we go through. Is that correct?
Yeah, that's exactly correct. And as you stated, which I should have mentioned, is there's never a void in the ground because the drill mud takes up all that space that was displaced by the reamer. So that mud fills that hole right where it says drill steel and swivel there. That entire hole will be full of drill mud, and the excess drill mud is being carried out to the exit side and then being recycled to be reused.
Okay, so it's slightly pressurized, that bore path is as we go through this. Okay,
Correct.
perfect, perfect. So then the pullback is when we're actually starting to, we've enlarged that opening, that bore path, to be able to be big enough to receive the pipe that we want to pull into place. And then now we start to go through that process again. Is there a step like swabbing between
Yeah.
that part and then pulling the pipe back?
Correct. Depending on the size of the pipe would depend on the size of the ream and how many reams you'd want to do. Different operators prefer different scenarios. Some drill operators prefer to go 0 to 30-inch right away. Some drill operators prefer to do a 12-inch ream, an 18-inch ream, a 30-inch ream. And the ground conditions really dictate what you're going to do there. But for all intents and purposes, correct. You ream to whatever size you're comfortable with, normally 50% larger than the product pipe you're going to install. So there's a little bit of give on each side. Then you'd normally pull a swab ream through, so it's to clear any leftover rocks or debris that might be in the hole. And then you move on to the product pipe pull, where you'd push the reamer back to the exit side. Your product pipe will be strung out, prepared to be pulled in, and then dragged in the ground. That process is normally, we like to do it in a 24-hour operation without stopping. The more downtime you have during the pullback, the more likely you are to lose that pipe. The ground may settle around it. You might build some pressure, and it can happen. So the least amount of time the pullback takes you, the better.
That's what they say about the trenchless operations. Once we start, we want to keep going there. So
Yeah.
there are lots of reference documents covering this technique and these progressions and design analysis as design engineers before we even get to moving any amount of equipment to the rig. Here's just some examples for you. The PPI Handbook on Polyethylene Pipe certainly gives you good guidance. ASTM standards do give a pretty good guidance for you as well. Here's essentially what we're looking at from a design standpoint. So civil engineers, pipeline engineers, geotechnical engineers out there, when we look at a project like this, we are going to be looking at the friction in 4 different spots. So that's going to be that S1, S2, S4, and S5 as we're pulling through this. And then what that friction force will translate to us is an allowable tensile force within the pipe. That tensile force comes from the industry itself. That's very well known from all of the pent testing, all of the testing to give us the hydrostatic design basis. And then it directly translates right to the allowable pull force for us within the cross-sectional area of that pipe. So again, we have a PSI that is the allowable tensile stress, and then the larger pipe we have, the thicker the cross-sectional area we have of that pipe. So now it translates to a larger force. If we're pulling with smaller pipe, it might not take as much pull force is a longer pipe through that. But these things are all considered when we are designing a directional drill through this process itself, and we continue to go through. So sometimes, John, the biggest thing I see some design engineers do that aren't familiar with horizontal directional drill is to try to have too steep an entrance or an exit angle. Try to get down as quickly as they possibly can to transpose or cover on whatever ground they want. Now, is that a limitation of the pipe, or is that a limitation of the equipment that's doing the work for us?
Yeah, it's a limitation of mainly of the steering tool on the end of the drill rod. The steering tool is probably the most sensitive part of the pilot bore process. It's just a long non-mag connection that it can't bend as as much as the drill rod can bend. I mean, the drill rod is steel. You'd be surprised how much it can bend. But the consideration is really about the steering tool at the end. You don't want to damage that, or God forbid, snap it off or twist it off. So correct, the entry angle and the exit angle are two big considerations when designing these.
All right, lots of questions coming through for everybody. We're really happy that you're asking those great questions for us. So here we'll talk about that friction as well. HDPE itself does float because its density is lower than water, and so sometimes we put fluid within the pipe itself to be able to lower that buoyancy and reduce that friction force as we come through. So we call that the capstan effect when it raises on those curves. And we do have the ability to estimate these and run through all sorts of different stuff for us. So here we got a question that we're going to answer live, John. For larger pipes over 24-inch to 30-inch, we have been directed to use shallower entry angles for pipe stability on the rig. Can you confirm that's still a best practice in the industry itself?
Yes, it is.
Well, Jeremy, you should be doing this presentation with us up here. Absolutely, you've already got it for us. So, great questions, everybody, as we go through. The next slide for us shows what we would see within the Plastic Pipe Institute Handbook on Polyethylene Pipe for safe pull force. So we do have a equation for that, and there's also an app for that that you would go online, and it's called Boraid. We may talk about that as well here, but. So, John, you had mentioned previously that the soil conditions on the existing site make a big difference as to how much material is removed or how quickly we can get through some things. Something tells me that geotechnical is probably pretty important in your plans analysis. Now, if an engineer out there did, one boring or just a simple USGS survey over what the soils there is that going to stop you from doing the drill, or is it just going to, maybe increase the price because of the risk a little bit?
Yeah, correct. Yeah, so the more test borings, the better. Right along the drill alignment is preferred, 50, 100 feet in either direction. It could be a big change. One bore on one side, not sufficient. And the more information we have, the more aggressive we can get with our bidding. The less information we have, obviously, the more we have to cover ourselves. So yeah, the geotechnical exploration is crucial to a successful project. So I mean, we always like to say the more the better, and if you can get them down 20 feet below, 25, 30 feet below where we're gonna install, that's preferred, because a lot of times these drills have to be redesigned for whatever reason. And insufficient geotechnical can really cost the project and the owner.
Okay, absolutely. So that is a boring as to which we take samples of the soil throughout. We're looking for changes in condition because the reaming head that they have, being able to push through the soil changes, may very well change in the type of reaming head that they actually use through this as well. What can you walk us through some of the risk considerations? When I look at another question here for.
Sure. Yes. I mean, the largest risk consideration is always your inadvertent release, or IR, frac out, whatever you want to call it. Essentially, that's when your drill mud builds up pressure underground and finds a path of least resistance and releases to the surface. All the drill additives and mud we use are organic, are safe for the environment, but a lot of times DEC or the EPA, they don't care. They still consider it an environmental hazard. As you can see in these photos here, the mud could kill wildlife. It could damage plants on the surface, even though it is environmentally safe. So the frack out and the IRs are a big consideration in our planning of a project. And that's a lot of times what we see when we get a design from an engineer is we'll say it needs to be deeper, or it needs to be generally not shallow, or generally deeper, just to alleviate some of that risk, and get the mud to make it back to the rig, and not, if you're shallow in the center somewhere under a body of water, finds an easier path and releases into the water, and you could have a real expensive and environmental disaster on your hands.
You're on mute, Pete. You're on mute, Peter. All right, so I'm going to step in with Pete because he's on mute. The question we had that he's trying to convey here is how close to level do these drill rigs need to be, and do they have leveling jacks or legs that can be adjusted? Is there some type of a sensor on the rig like you would put on a crane that if it is out of level that it would shut down? Those are very specific questions.
Yeah, I mean, there's depth. Oh, so the answer is as level as possible, right? Generally, we require a level surface. With the big rigs, we require a lot of times timber matting to keep the area clean. And yes, it needs to be level. All makes and models are different. I'm sure there are models out there that have kill switches and things that shut them down if they're not perfectly level, but most of them do not. But as level as we can is what we want them to be.
Absolutely. So, an important note is the only step on the bore path that is intelligent is when we're first putting that tool in the ground to come through that tracks our location of our bore path very specifically. After that, that's been established. So, any of the reaming that we have follows along that bore path and just simply removes material and expands that as we continue to go through. We're going to talk for just a quick second about restraint. So there's a big difference between thrust restraint and anchor restraint. Thrust restraint historically in pipe design happened to be some type of a thrust block around changes in direction or bell and spigoted pipe due to surge within the pipe itself. So that's focused on not blowing off the bell and spigot pipe from a surge event within the inside of the pipeline itself. Since HDPE is a fully restrained system, those fuse joints are simply not going to do that. But when we're done with the pipe, from a horizontal directional drill standpoint, we want to make sure that it's restrained in its full connection at the tail ends to be able to stop from pull out. The mechanisms we have from pulling out from a bell and spigot system on the terminal connections happen to be anchor blocks like you're seeing here, or an electrofusion thrust restraint. So you simply put that on the side of the pipe and fuse it onto the pipe and embed that in concrete. And we're going to make sure that any type of thermal effect or Poisson's effect is, as you saw in the opening video, does not pull a bell and spigoted pipe system out of its bell and spigot. Now, of course, big picture wise, you want to be HDPE through the entire thing. However, sometimes design engineers and municipalities want to transition back to PVC, and they would use some of these restraints as we go through. You want to tell us about this Champlain Hudson Power Express project? It sounded like it was monumental, and it was a pretty cool thing to work on, especially with the company, right?
Yeah, that's correct. Yeah, so this is the Champlain Hudson Power Express. Can't get really into too many of the details, but I'll speak of what's been, publicly released. It's the largest renewable electric project in the country. The general contractor in charge was Kiewit, and we were lucky enough to be selected as one of the 4 directional drilling contractors on the project. Now, we had roughly 100 drills throughout the center area of the job, all around in and around the Albany area, slightly north of Albany, slightly south of Albany. But it was a great project for us, and yeah, it's coming to a close now. So successful on all fronts.
That looks like a heck of a long way to be able to go there, from one location to the next. So that's one heck of an investment to be able to bring all that electricity to New York City and Long Island area. You're out in
Right,
Long
yeah.
Island, aren't you?
Yeah, exactly. Yeah, just to be clear, I mean, the whole job was not directional drilling. A lot of it was open cut. A lot of it was strung in the river, and the directional drilling would just be to get in and out of the river or cross a body of water or sensitive area.
Sure, sure. You can't do a project like this without lots of different mechanisms through it. So,
Right.
yeah, it takes about 6 hours to drive that route. So there's a whole lot of ground to cover between it. Definitely a lot of interesting project considerations to get from point A to point B. And that technology that we have with horizontal directional drill is going to minimize that environmental impact and do a lot of those great things that trenchless really brings to us. Not only that, but it was pretty aggressive, wasn't it, John?
Yeah, it was. Yeah, all the contractors had a performance clause, and completion and project success was definitely at the forefront in everybody's mind the whole time.
Absolutely. That's a lot of pipe to get in place and a
Yeah.
lot of construction to be able to put in a small amount of time. So,
Yep.
here is some equipment. Can you just tell us what we're looking at?
Sure. This is a Vermeer 100 directional drill rig, kind of a middle of the road, medium sized drill. Use this for like a production style drilling down a street. Up to about, a 20-inch bore, you'd feel comfortable doing with this. You could go bigger, but if you really strain in the machine, this would be for like maybe 2 6s, 3 6s, right down a road for like an electrical bank, something like that. The excavator there supporting the drill, loading the rod baskets. The rods that go into the ground are installed on the drill in baskets. So they're not all on the drill at the same time, and then the drill loads them one after another as you pile it out. Behind the drill there, that's a tanker holding the mud that gets pumped into the drill, the mud that displaces the soil in the ground.
All right, so this is circulating behind this, and you're removing it and trying to keep as much of the actual roadway surface minimized for its closure as you're going through it. Is that correct?
Correct. Yeah. So you can't see the cleaner in this picture, the reclaimer that's in a parking lot next door, but the mud would be trucked to the reclaimer, then cleaned and trucked back to the that silver tanker trailer there, pumped into the tanker trailer, and then pumped back to the drill. Then back to the cleaner, back to the drill. Same drill at a different angle. Pretty cool shot there with the airport radar dish in the background.
Here's some of
Um,
those timber things that you were talking about, correct?
Yep, correct. Timber matting. Yep, this is from the Champlain Hudson project. Yeah, nice big safe area to work in. Everything's kept clean, everything's kept away from the drill rods. This is generally what we require and expect when we figure on setting up on a drill site.
So when we're doing a HDD, sometimes we are forced to do that because it's a challenging install. And you could see here that the above ground conditions needed additional handling in order to be able to even get the construction equipment there. So some intelligent people within our industries, have asked previously, if you're going to do something for the most difficult installation, why don't we just use HDPE for everything else as well? But sometimes it doesn't work that way. But let me get to the next picture. What are we looking at here?
This is a drill rig on another site up here in New York. Just drilled under a river, and that is the end of the ream. That's the reamer there, with the product pipe just sticking out of the mud. After a successful install.
So here's that reamer. This is what enlarges that bore path as we come through, and it directly connects to the product pipe we're pulling. And then now, by the time that we got to this process, everybody's pretty happy, right?
Yeah, this is a happy day, and it's still light out, so it didn't take us all night to do it. So that's even better. Same drill, same job at a different angle. you can see, to answer the individual's question from before, everything's as level and as straight and as flat as we can get it, you know, try to keep everything organized and clean and safe.
So here I see this attachment on this backhoe here. This is something special for the drill string to load it up into the machine, correct?
Yeah, that's called a deckhand. That grabs the drill rod. The drill rods are all lined up on the ground there. And as the drills get either drilled in or pulled out of the ground, that grabs them off of the rack and either takes them off or puts them on the drill.
All right. So here's a video. Let's see what we're looking at here in this scenario. Go ahead and talk through it.
Yep, this is from inside the drill cab. This is the operator as we're finishing up a install in rock in New York City. This is the view that the operator has the whole time. And where the white part of the, yep, there's a better view of it there. So he's able to see the whole drill rod going up the rack. You can see the vices moving there. If you take a look at that reamer, that's a rock reamer. Talk about ground conditions. Every ground condition requires a different reamer, and can really affect the pricing. So to know what's in the ground before we start is critical. Some of those reamers could be 3 times what another one costs. So it really to alleviate the stress on the job, the more investigation into the geos, the better.
So that's circling back to what we had talked about earlier, in that geotechnical investigation gives the contractor and the drilling subcontractor the ability to understand what's in ground surface conditions underneath ground, which we don't always know. And in this particular one, I believe when John first started talking to me about this particular project, the time that it went required to be able to put a single drill string or drill rod into the ground through this particularly hard ground condition just made my eyes go like this. Like, really? What was it, like 30 hours for? I don't remember.
Yeah, it's been a while for me now. But yeah, this was some of the hardest rock that definitely me, but even a lot of our staff who have been in the industry for 20, 30 years, the hardest rock they've ever drilled through, and in New York, go figure, right? New York City. And yeah, 30 hours per rod. I mean, the whole project probably, don't quote me, but I think 3 or 4 months of steady drilling to pilot out and then open the hole 1,600 feet.
All right, we've had some really good questions. Hopefully, all of this nuts and bolts type of discussion really helped get through everything in that process. So here's just another way to be able to what are we trying to do here, John? Obviously, we're not pulling it on the surface, but that was
Yeah.
probably a requirement, right?
Yeah, so this is one of my favorite photos. This is that river crossing in New York City that we talked about earlier. And yeah, this is the product pipe. Not allowed to touch the ground. So you can see the guardrail we have to string over. And the only place to string the pipe out in one solid length was down the side of that building you're looking at. So we fused it down that road. And then to pull it into place, we used these suspended rollers with excavators and front loaders and did this reverse curve. And right where I'm standing there, taking the photo, is where it's entering the ground. So pretty monumental. And then down that whole string, down that whole run down the side of that building, it's suspended on rollers as well.
Okay, so we had some questions as to why wasn't the pipe allowed to touch the ground. Sometimes various municipalities or clients have specifications that, you know, that they didn't review the Alliance for PE pipe specifications in part of this, and they have other understandings or other preconceived notions about HDPE through this process. Now, just to make it easy and level the playing field, HDPE has the most forgivable allowable bending radius of any of the pipe material types. Steel, you would often go through this extent in order to be able to properly install steel and not stress its allowable bending radius. But any type of gouge on the surface of an HDPE pipe, if it's beyond the 10% of that wall thickness, then we'd have to cut that section out. But different clients require different things, and John just wants to get a project done at the end of the day. So, Pete, let's try your microphone again. Let's see if we got you.
Yeah, it's working this time. Thanks. So John, I mean, obviously, I wouldn't consider this a best practice because, there's a lot of expense associated with using capital equipment with those lifts on it. I would prefer to see some pipe rollers, which are really standard items, so you could just pull it along the ground. Would you agree?
I would agree, Peter. In this particular instance, I think if you'll notice that guardrail underneath it there, that probably had a lot to do with the planning behind this, and just being able to make that reverse curve around side of that building. But there are standard rollers going down the side of the building for the vast majority of the
Got
string
it.
of the pipe
Okay.
string.
Thank you, John. Great presentation.
So we're a little bit behind, but not too much, John. So you're just fusing on the pull head right here. Is that right?
That's correct. The picture on the right is the pull head being fused onto that pipe we just looked at in that reverse curve.
Okay. Okay. Perfect. And what are we looking at here?
This is the same job, casing pipe, with large pipe on the outside, and the carrier pipe bundle is being dragged through. The customer wanted a carrier pipe, casing pipe configuration. So we pull the big pipe in, push the drill rods back through, then pull the little pipes through the inside. And you'll notice on the photo on the right, there are rollers banded together, banding the bundle together. This is just how it was designed, so that's how we installed it.
Okay. Okay. That's right. Sometimes we just don't buck what they want to do. We just do it, right?
That's right.
All sorts of things capable here. So here's the same type of principle that we had just discussed. Now we're just translating that allowable tensile force across multiple pipes as we pulled this through. Once that bore path is in fact established through that drilling process and we get through that rock that John had talked about, sometimes these lengths of these bores are pretty typical as we're coming through, and we're not going to damage that product pipe in any way, shape, or form. So here's another shot of the reamer and a pull head from an opposite side looking at it, and that's a good day for you.
Yep, yeah, it's another successful pull day. Same job, just a different angle. You take a good look at that rock reamer there. That's a pretty cool picture.
All right, so it can be a little messy, but so is pouring concrete. This is just a lot easier than pouring concrete in that way. John, thank you so very much. Any other questions that you might have out there? John is going to be available to answer that question for you on the bench for the rest of us. I'm going to cruise through pipe bursting, compressive fit, and slip lining pretty quickly, and then we'll have time for Ryan to be able to cover a lot of different ground for us. So pipe bursting is another trenchless technology method that basically does three things simultaneously. It fractures the existing pipe. It creates a temporary soil cavity within or surrounding that existing pipe, and then it pulls back that replacement pipeline as we go through. That pipe fragment is simply pushed into the 2 to 3 inches of soil that surround that replacement pipe, and it is the only trenchless technology rehabilitation method that can put back a larger OD pipe than what is there existing. So very well proven throughout the United States. A lot of technology done throughout the United States as well. And there's a significant amount of pipe that really is replaced through this method. So here's a good example of just cast iron pipe being fractured. Cast iron pipe is easily fracturable in that manner, and those pipe fragments simply break and come through, and then that pipe fragment stays within the 2 to 3 inches of soil surrounding the pipe. The technology itself was invented in British gas and brought over to the U.S. in early 2000s. The patent protection was lapsed in the United States, so then it became a lot more popular after that as well. British Gas studied these first pipe fragments by overpulling a meter-long section of pipe in front to see if those cast iron pipe fragments did gouge the pipe, and it did not as it comes through. But it really is just as simple as you see here. Once you start to burst something, it's kind of like watching paint dry as we come through. So you can do clay tile, PVC, concrete. Reinforced concrete has a reinforcement around it, so it's typically not going to be able to be burst. Asbestos cement pipe is easily burst. Those reinforced pipes, like a pre-stressed concrete cylinder pipe or something similar in that nature, are going to be difficult to be able to burst. Ductile iron has different characteristics than cast iron, and it'll actually want to elongate and stretch at that fracture point and then try to close back on itself. So that is in developmental phrase, we are going to cut through steel or other type of non-fracturable pipe material as we go through. It is in the family of trenchless technologies. So we are looking at 85% or less of excavation through this process. And what you'll see here on the left picture happens to be a receiving pit. So that's where we're going to put the static bursting machine. Two different types of pipe bursting equipment. One is pneumatic that uses an impact hammer that's powered by compressed air. That technology only uses high density polyethylene because of the pneumatic movement, as we're just consistently pushing through that. And static bursting uses a rod to transmit that force, pulls that expander head as soon as it's come to the other side of the pipeline, and just brings back that expander head and the production pipeline at the same time. That's what we're seeing here with this static rig. And then all the way down on the other side, that's when we're putting in this insertion pit. So in suburban and urban areas, I liken this to surgical excavation, in the fact that if we had 5 services on this line, we'd have the machine pit that's about 4 feet by 8 foot. If we're in the 3 to 4 foot, 3 to 5 foot depth range for the pipe, on the other side, we're going to have a 4 foot by 4 foot pit for the pipe to get in. And then each service connection is only going to be about that same size. So if we have 1,000 feet run, we're really looking at about 32 feet worth of excavation throughout that whole process. And we're going to use HDPE's ability to be long fused runs in advance to be highly productive. It's very routine to be able to fuse up 500 feet to pull in at one time from an offsite job area itself. And then you'll see in the video on the right, this is actually moving it from that laydown yard all the way through this process to the job site. That's a temporary thing as we go through. The industry itself has productivity tools and equipment to be able to make sure that you can get one crew member fusing up very long runs of pipe to be able to do this. What you're looking at now is called a pre-chlorinated pipe bursting process, where we are disinfecting and pressure testing that pipe in advance of pulling it into place by taking 2 days of bacteriological samples that show, yes, this pipe interior is in fact free of total coliform bacteria. We're showing that it is properly disinfected. In the day of the pull, we'll drain the pipe, pull it into place, and flush it again with superchlorinated water and turn it right into a service itself. So here's a couple of images as the pipe string. You can see the allowable bending radius is very, very forgiving for us in order to be able to allow us to move this pipe into place easily. We've got a great question here for us. What type of typical ground heaves can be expected when pipe bursting? It's contained in the near pipe boundary condition. Does it propagate through the soil column? So I'll go right to the answer and then talk about the theory a little bit. So the industry rule of thumb is for every inch that expander head is larger than the existing OD of the pipe, then you need 1 foot of soil to accommodate any ground displacement through that. When we're shallow, all of that soil displacement could be projected upwards. When we're deeper, now we have a lot more soil density and soil weight on top of that column, in which case it'll be directed outward and upward through that process. Contractors have lots of tricks up their sleeve in order to be able to stop heave as well. I've certainly seen them put a steel plate on a surface areas to which they didn't want to restore, and then park the dump truck right over top of it. So we're going to, push that down. But really, we're looking at originally compacted backfill to be the best soil condition for us. The worst are going to be a rock condition, in which case we couldn't get that expander head in through that process as well. Great questions. Here's simply moving it from the laydown yard to the actual installation itself. The actual act of pushing rods or cable out into 400, 500 feet of pipe could take about an hour. And then the process of pulling all of that back through the pipe bursting process could take about 45 minutes to an hour as well. So this pipe string is not going to be in front of everybody for that long, because it actually happens pretty darn quick. Most of the work is infusing the pipe. Most of the work is in restoration and all sorts of other things through that process as we go through. Slip lining is very similar in our setup. We need to decommission the pipe, provide access to it. Difference here is we're going to clean out the interior of that pipe, as now we need a properly prepared interior ID to pull that pipe into place for us. So we don't need an obstruction to be able to stop us from pulling that pipe into place. So we need it to be properly prepared through that. All of this setup is going to be similar to pipe bursting, where we're going to fuse long runs in advance. Here's just some images and also some video of being able to pull this in place. What you're seeing on the right there happens to be a reinforced concrete pipe that was in the Miami area that was slip lined. The actual process of putting this 400 or 500 feet worth of pipe happened very quickly through that process. They just started to push it, went in easily, and HDP is a perfect use for this process as well. Here's some a reuse of a pre-stressed concrete cylinder pipe that they thought was failed and lost forever in Suahirita in Tucson water. Essentially, this pre-stressed concrete cylinder pipe was leaking, had several repairs. It is 24-inch and 30-inch, so they had simply abandoned it, and then they attended, one of our webinars through this process and saw that they could come back through and repurpose this. The story here is it did provide a 10 MGD, a million gallons a day of conveyance for new potable water supply system as we went through this process here itself. These videos are really showing how we're pulling that through a properly prepared surface. We're simply taking advantage of those beneficial properties of high-density polyethylene and its ruggedness and durability. You could see here, we are still pulling it through what otherwise would have been a bend, a fitting in the actual existing pipeline. They just remove the fitting. They remove the soil surrounding it. And then they're simply just pulling that through that area. We're not stressing the pipe. We are not pushing it outside of its allowable bending radius. And when it's settled, not under stress anymore, it's definitely going to be a happy pipe and not beyond its allowable limits there as well. So here's another video. We're simply making sure that we are properly aligned and that idea of the pipe is properly prepared for what we need it to be, pulling it into place, and that's as simple as really that gets in that manner as well. So compressive fit slip lining is the same thing as slip lining, but we are actually taking the HDPE, making the OD smaller temporarily, pulling it into a place, and then allowing it to relax and regain its shape as well. So it does push against the ID of the existing pipe. A lot of times engineers will look at slip lining and say, well, I don't want the reduced ID. This happens to be the solution for that problem. This is HDPE is the only product pipe that is used to be able to do that process here. And here's a very good example of this dye reducer itself. So they do spray an oil on top of the pipe to help lubricate this. It is a 32-inch OD HDPE that's pulled into 30-inch cast iron pipe, 29 inches under tension. A difference between this and pipe bursting is there's a lot of force that's happening at this dye reducer, and so it needs to be able to push up against something pretty strong to resist that force as we go through. Here's just another video of this process itself. This is happening all over the United States. Pre-stressed concrete cylinder pipe, reinforced concrete pipe, other things, projects of that nature as we go through. And there, I'm done. Ryan, you still with us? You want to take over for, I know we've got about 20 minutes to do open cut above ground marine and plow in, but I know you're up to the task. It's a little daunting, but I know you could maybe talk like one of those guys at the auctions if you need to, right?
Ah, I wish I had those skills, but no, we should be able to get through this section pretty quickly. So when talking about open cut, we look at trench width requirements with open cut. So uh, ASTM D 2321 talks about the trench width and open cut standards for HDPE pipe. And here's an example here. So if you look at this chart here, from 3-inch to 24-inch nominal pipe size for HDPE, you're looking at the OD of the pipe plus 12 inches on the width. So 10-inch IPS needs a 22-inch trench. We're going to add that 12 inches to the 10-inch OD to have that 22-inch minimum. So 24-inch bucket would be typical for a pipe of this size with HDPE. Embedment requirements also covered in D2321. So this is going to be, this slide will talk about max particle sizes with nominal size HDPE. So, looking at these pictures on the left, we can see the trench has been excavated. The HDPE pipe has been laid into the trench, and they're starting the backfill of the pipe. So this chart would show, for say a 6-inch to 8-inch pipe, the max particle size, so maximum would be 3/4 inch. So a 10-inch IPS would permit a 1-inch particle size for its maximum.
So I wanted to point out that 6 to 8 inch pipe, as you just said, Ryan. Oftentimes, if we have groundwater in the bottom of an excavation, we'll put down what's called a 57 stone. 57 stone is that's the sieve that it comes through. It's crushed rock or crushed gravel or things of that nature, and that's about that 3/4 inch particle size. So what we use to stabilize the bottom of the trench is still perfectly usable along a 6 to 8 inch pipe, and it's not going to hurt that pipe. So that's one of the reasons why we call that particular process out. It's very, very common to be able to stabilize the bottom of an excavation. It's not for the pipe's sake, but it's for the people that are doing the work on the pipe itself. So keep going. Doing great.
And you can use that same rock for your backfill around the pipe, correct? That you're putting on the, yep.
Absolutely.
So here is a video here of a trench open. They got a guy down in the trench directing the operator of this equipment with the bucket on it, and he is adding some of the backfill or bedding into the trench before they lay the HDPE pipe down into the trench. So they're getting things prepared for the installation of the HDPE pipe.
So I like to show these types of videos because oftentimes some people will go aghast at it, but we are reducing the amount of people in the excavation. It's there for the pipe, but we don't need a whole bunch of people in that excavation, which makes it highly productive. We'll have another video a little bit later showing the preparation or pushing the pipe into place just prior to be able to put it, obviously do the backfill and compaction. So once we recognize, Ryan, that we've got those long install areas of fused pipe, here's another method as to which we can really maximize our productivity, correct?
Correct. Yeah. So here you can see the trench has been dug, and the HDPE more than likely is being fused together in lay lengths at a certain length needed for the trench. And so while you're digging the trench, you can have a company like ISCO out there with HDPE fusion equipment preparing the HDPE pipe for install. So kind of a double whammy of labor efforts going on at the same time that can help potentially reduce the schedule of the job. So pretty large diameter pipe there. It was a great picture on the right. So a lot of what we were looking at on that last slide was HDPE being fused above the trench, right? And then installed down into the ditch. There are needs for in-ditch butt fusion, maybe for a tie-in, tight work area where you need to put a fitting in, multitude of reasons. So is in-ditch butt fusion possible? Yes, yes, it is. So here's a good picture here, center to the right. In the background, you can see the track machine, or that would be the chassis of the machine, and the carriage or the operation of the HDPE fusion is in this carriage assembly here. So you can remove the carriage from the chassis. The track and the chassis and your power will stay above the trench on ground, and then you can lower the fusion operation part of the fusion machine down into the trench. What we'll do is we'll provide extension hoses, hydraulic extension hoses, that'll connect the carriage back to the vehicle there, so you can continue to provide hydraulic fluid, right, for the operation of the fusion machine. So it's possible. This is a 3-jaw setup that they're using here, as you can see in the background. The 4th jaw of the machine stayed on the machine. You can certainly do it in this configuration. There's also ways to do it with 4 jaws. It just depends on your footprint and your layout down in the trench on what you can put down there. So we can put the whole machine down there if we need to, but that is a typical in-ditch method there. Yeah, there's another picture on the right, large diameter fusion machine going in trench to, so this would be a 4-jaw setup going down into the trench there.
Whoops, there you go. I'm not muted now. All of these machines are in fact designed to be able to be removed from the chassis and lowered down in the excavation for these butt fusion. Yeah,
That's correct. Yep, that's for those limited access, tight areas where we were able to go down in there and do HDPE butt fusion. So here's talking about flexible pipes versus rigid pipes, and showing that load induced stress, right? So for the flexible pipes, you've got your ductile iron pipe, your PVC, and your HDPE, all fall into the same category as far as you've got that stabilized passive resistant pushing back on the pipes as that load is induced, say HS20 loads being compressed down onto the top of the pipe. You're going to have that passive resistant pushing back on the pipe to keep it from wanting to elongate or potentially coming out of round, versus your rigid pipes, your weaker soil resistance, but you have a rigid wall, so you're not worried about that compression or that load being pushed down on those rigid pipes like you are with flexible pipes.
awesome. Awesome. So here's another video that I was talking about here. Once they properly prepared the bottom or the foundation, foundation of that trench happens to be an area that's free and clear of rocks or other things that could potentially hurt the pipe. And then that bedding that we saw being put in earlier. Now you can see he's obviously not in the excavation. We're simply pushing that fused pipe over. I remember, Ryan, when Peter first put this video on social media, everybody had a field day with it, but there's nothing wrong with this. This is a very highly productive manner of being able to put in pipe into place with less crew in that operation. We're obviously digging less, we're impacting things less, and we're simply having a paradigm shift about how we install pipe to be able to take advantage of that long fused area that we're looking at for a longer run of pipe in that manner. So here, AWWA gives us a design window. Not this most recent issue. They talk about an engineered installation versus a basic installation. It means the same thing. But a basic installation happens to be if we're DR7 through DR21, we have a minimum depth of cover with that box truck loading that Ryan was talking about. So if you were part of a road show and you see Bob driving the Penske all the way over there, that's exactly what that box truck is, with 10,000 pounds worth of gear coming to you so you can touch it and feel it. That's that 3 foot of cover that we want minimum. If we don't have that Penske on top of the pipe, then we have 2 feet of cover. And then if you're less than 25 feet deep, you don't have to do anything. You don't have to worry about it. You don't have to do install calculations. But if you really wanted to do the install calculations, just reach out to us, dlandy at pepipe.org, jstevens at pepipe.org, or just send us an email right now. We'll send you over that spreadsheet so you could take a look at it. So some of the interesting things here, Ryan, that make this type of pipe material different from others, or its viscoelastic behavior, but also thermal expansion and contraction. You want to elaborate a little bit for us?
Certainly, yeah. So the way I remember this one is the 110-100 rule. So PE expands and contracts at a rate of about 1 inch per 10 degrees of temperature change per 100 feet of pipe. So if you're looking down here at the example for HDPE pipe, you've got 2-inch DR11 HDPE pipe at a length of 200 feet with a delta in temperature of 40 degrees. So if we go back to the 110-100 rule, apply that 40-degree temperature swing. That's going to have a 4-inch change in direction. So that's per 100 feet. In this example, we've got 200 feet of pipe. So we multiply that 4 inches times 2, and it gives us a total of 8 inches in growth or contraction. So another thing to point out here, PE requires a much smaller force to restrain expansion and contraction compared to other materials. So in this instance, we had 321 pounds of foot-pounds of load between the growth or shrinkage of the HDPE pipe versus carbon steel pipe, much more rigid, stiff pipe. Same scenario here, but generates 8,067 pounds of force. So a lot of force there generated versus HDPE pipe generating a much smaller force. And I believe you talked about earlier some of the restraining methods where we can do wall anchors or electrofusion flex restraints to basically create a thrust block for controlling some of these thermal effects with HDPE.
We did, absolutely. So once we have that fully restrained system, any type of change. With an installed system, what we're primarily looking at is conveyed fluid change. So if our temperature of our water changes, which does happen, but it is rare. But in temporary conditions, we're looking at moving the pipe from above ground to below ground, and then we're trying to find stability in that process. So the big thing here is the modulus of elasticity is lower than the other pipe material types. So while it can move more because of that higher coefficient of thermal expansion, the actual force required to stop it from moving is significantly less. So the phenomena that does this for us is that 2% carbon black. 2% carbon black entrained in the resin. What it does is it wants to try to move while it's in that pipe wall. So that's actually diffusing that UV radiation. So don't get an image in your head that the pipe wall is moving. That's not what happens. This comes from our chemical engineer people that tell us that all of that's entrained and trapped into the actual pipe wall. But what that does for us is provide us limitless UV protection. So this pipe can be above ground for its entirety of its life, reused and reused and reused in mining operations or sanitary sewer bypass operations and other things. And that is a particular attribute that we really, really like. So moving straight into above grade here, Ryan, I know you've done some of this with ISCO. Keep going, bud. You're doing great.
Yeah, so we work with some of the temporary bypass providers, whether they're providing potable water, gravity sewer, things like that. But you'll have an area of work where there's some rehab where lines need to be isolated or shut down for repair or for maintenance. And we work with multiple contractors or companies that'll go in and create these above grade temporary bypasses to provide potable water to businesses and homes, providing that sewer and things like that. So HDP is not just a below grade pipe. We use it every day above grade as well. Yep. So here's a picture of a temporary wastewater line using pumping. So, creativity here, temporary pipeline location. So going right through this ditch here, through the drainage structure there into the road. HDB can bend, flex, you can pull it. I think the video earlier showed that excavator just pushing the pipe into the trench without damage to the pipe. So very, very tough HDP. These temporary bypasses typically are reused pipe where they install, demobilize, move it to another site, refuse it, and just continue to use it over and over again. So yeah, that picture was a really good one. If you go back to that, Alan.
Sorry. Yep, we're got
Running out
about
of time?
5 minutes
Okay.
left. So no,
Yeah.
but definitely
You know,
talk us
but
through
no,
this
that-
one because that is it.
Yeah, that was just a great picture of just the ability of HDP pipe with the manifold and just the tight work area. It's a very light pipe for the contractor to handle. So they're able to do these very tight space setups like this with pumps and pipe and valves. It's just truly creative there on what that job did for Baltimore.
All right, here's Marine.
Yeah, so marine's a valuable method when you can't utilize HDD. It could be due to a marsh, swamp, bayou. I'm originally from Louisiana, so I know a lot about those bayous and swamplands. So not a lot of structural integrity, as I've found out in my youth when I used to try to walk through a marsh or a swamp. You don't float very well, you sink. But HDP pipe will float. So another example would be pipeline too long to drill there. So HDP is buoyant, right? We talked about that earlier with the HDD. Sometimes you need to fill the pipe void with fluid to anchor it down. So same thing here, but with HDPE, you can fuse it together and tow it across the waterway for install. Really, really useful when you don't have a lot of laydown space or area to work in. You can just build these pipe strings and then put it on a tow and tow it across the waterway to the job site. So very impressive pictures there. And the picture before showed, and this one shows it here, these concrete anchors, right, that they're installing onto the HDP pipe. So when it is time to fill the pipe with fluid, it'll allow it to sink to the bottom of the waterway there.
Yeah, good point, Ryan. Hey, Alan, one of our friends down in South Carolina mentioned maybe we should talk about those electrofusion flexible restraints. Could you tell us a little bit about the role that they play, or Ryan, and how that can be helpful when we're using a anchor block?
That way, go for it, Ryan. Absolutely.
Yeah, talking about the electrofusion flex restraints and how they're utilized. Yeah, so electrofusion flex restraints are quite small. They are electrofused. There's copper coils within the flex restraint itself, and they fuse to the outer pipe wall. Each one is good for a certain axial load of resistance. Some are 7,000, some are 9,000 or more. Once you determine, the engineer will determine the total axial load that they're wanting to resist there in that thrust block. That's how many electrofusion flex restraints we figure out we need to add. So, if you've got 90,000 foot-pounds of force and we've got 9,000 foot-pound axial load on the flex restraints, we'll put 9 of them. 10 of them. And yeah, they're very easy to install. Once the pipe is set, we typically come in, and that's when we install the electrofusion flex restraints. And then the contractor will form up to pour his concrete block around the HDPE pipe that now has those flex restraints installed.
Awesome. Very thorough. I didn't even have to be here, Ryan. You got it. Absolutely.
I might have done it once or twice, maybe once or twice.
Tell us a little bit about plow in. So this is another kind of freak of nature of using HDP in rural areas.
Yeah, so I've yet to do this in my career, but I understand the methods. It's like you mentioned, rural areas where you have a lot of area you can work in, even though this right of way is pretty tight. You're running long stretches of HDP, right? Miles and miles of pipe where you can use these plow-in machines that literally cut the trench and lay the pipe in. And you can do multiple pipes. You can do a 4-inch gas PE pipe with a 2-inch telecom conduit while laying the tracer wire and caution tape all at the same time with this plow machine. So there is no open cut, putting pipe in and then backfilling. This machine and this operation is doing it all for you at once. So That's
Spider
really
plow is-
impressive. Spider plow. So this one, is doing some pretty large HDPE pipe there in that this video here. That's impressive for that plow to put the large HDPE pipe in the ground like that. That's some heavy duty equipment for sure. Yeah, it's impressive. Look at the flexibility of HDPE there, able to go right into the ground, trenching it at the same time. So
Yeah, that'll do
very-
24 inches down to a depth of 10 feet.
that's impressive. Yeah, look at the scale. The guy in the background looks pretty small next to that equipment. So
Yeah, Matt Danish, come on. I wanted to say thank you to all of our participants today for helping us put this together, and particularly to Agru for your great support of the Alliance in this show. So Matt Danish, thank you for that. John Shumchick, excellent job. Ryan Ruiz, great as always. And Alan, thank you for carrying the day.